Hello. Dick and I have been doing some work on the Ventus anemometer that he bought, this one. And this video is about the modifications and tests that we've done to date in order to get a device to show us where the wind is working on the boat, but only for test purposes, because it obviously isn't waterproof. Well, this is the inside of the wind sensor. The vane goes on there and the anemometer goes at the bottom end. This is the 434 megahertz transmitter with the RF signal coming on this red line to here, where it goes down to a spiral antenna. Conveniently, it says ground data, VCC and power on these four connections here. So I soldered these two wires to ground and data and looked at the data on a scope. Basically what this unit does is it sleeps drawing 8 microamps for 70 seconds, and then it wakes up and it makes a transmission, during which time it draws 6 milliamps, and then it goes back to sleep again. I found a PDF on the internet which explains, although it doesn't actually mention this particular sensor, it explains the kind of the way that the data is encoded. So I reckon that if I put a lot of effort into it, I could work that out. The thing that worries me more is that it only takes one reading every 70 seconds. And I'd rather be able to read it once every 10 seconds, or even perhaps faster than that. So Dick suggested to me that maybe we should just take this electronics apart and just use the sensors and connect them directly down to the micromite. The sensor for the wind vane I can't see yet because I haven't yet taken this board off. The sensor for the anemometer is this thing here, which has just 2 wires connected to it, and I guess it must be a Hall effect sensor with nothing clever down there. I have undone these 3 screws, this one, that one and that one, but I still can't get the circuit board out. I think I'm going to have to unsolder the helical antenna from there, and also unsolder 2 wires here that come from the Hall effect sensor for the anemometer, and unsolder these 2 wires which are the power supply, which comes directly from the batteries here. So I think all of that is holding this down. Right, well, I've unsoldered that, and what we have here is what looks like a 4-bit sensor. 1, 2, 3, 4 bits, binary coded, and there is here on the underside of this PC board an LED which fits in that slot there, and thereby puts some light underneath this. And then on the top side of the board we've got 4 photocells there. So, and there's nothing else underneath of much interest. So I can only assume that the business end is in this black sort of encapsulated thing. This black encapsulated thing has most of the stuff on it, and it also has what looks like a crystal here. So what I could do is just junk all this, tap into these 4 photocells, tap into the Hall effect sensor, and then we could get the data directly, because A, we've got the complexity of decoding the way this serializes the data, and B, we've got the fact that it only wakes up once every 70 seconds. It'd be interesting to know how that works. And I can see there's a capacitor here. That might be a smoothing capacitor, but I mean decoupling capacitor, or it might be a timing capacitor. I think Dick is probably right that for our purposes, the simplest thing is to tap into the sensors and throw away the rest of the circuit. I had assumed that the wind speed sensor would be some kind of Hall effect device, but looking at it, it's only got 2 wires connected to it. And the PC board down here has the word read on it, so I thought maybe it's just a read magnetic switch, and indeed that seems to be what it is. So that's good insofar as it makes it much easier to decode, but on the other hand it's going to wear out sooner, I guess. Regarding the wind direction sensor, I showed you this 4-bit digital sensor that is built into the Ventus unit. So that's sensing the wind angle to the nearest 22.5 degrees, i.e. north, north-northeast, northeast, east-northeast, east. I thought that that was not really good enough because it just creates a 22.5 degree change as it moves from one point of the compass to the next, and then there's a 22.5 degree deadband where you can't tell if the wind's changing at all. So it's a kind of non-linear effect. So when Dick was here and we were playing with the leaf blower, we decided to throw this sensor away, and what I've done is I put a Bourne's EMS 22A sensor in its place, which will just fit in if I bend the pins over. This senses 1024 points around the 360 degree compass and gives an absolute readout. And I've turned a little doofer on. Some bastard is ringing me up, and it's bound to be about PPI insurance. I've turned 22. What have I done? I've turned a piece of Delrin to fix on here, and that seems to be working okay. So what I've got now to do is to wire it up and connect it to the microwave. Right, well I've put that all together again with a cable and tested it on this micromite, and it works okay. And I've rigged up a portable test rig with a battery here just to test the anemometer part of the thing, and I'm measuring the frequency on there. So if I start it going, well, that's not right. What's wrong now? Why does everything always go wrong when you try and test it? So if we rotate this, let's just reset that. I can't get it up much above 15 Hertz, and goes down to quite low. I should put the measurement time up. Well, with care it will measure down to half a cycle.
Okay, filming. Right, that's Peter syncing the cameras before. Can you clap? Actually, Peter.
Yeah.
Can you give me another one down there within shot in case the. Right. Okay. In case the.
Okay, we've got to get this up here quickly before everything goes.
Right. Okay.
Pear-shaped.
Right, so if I put this camera...
Don't close it and don't turn it off.
No. Right.
There's only one thing wrong with it.
What's that?
Back to front. The whole unit is back to front. I don't believe.
Well, does it matter?
Yeah.
Oh, yeah, it does for the wind thingy. Do I need a battery on there?
I brought two.
Can I go in this one?
Yes.
This one. It's ticking round, it's going round at the moment, but it's not showing anything.
Oh dear. It's happened before, but shouldn't happen. Is it going round up there?
Very slowly.
As long as it is rotating.
Yeah. So even a slow rotation would still show with it.
It's not rotating at all.
Oh, it was when I looked just now.
Well,
and now it's not displaying anything.
you mustn't press that button, because I have to do this, this and this.
Right, okay. You have a look and I'll try and give it a whirl with something. Oh, it's going round quickly now.
Well, I've had this before, but of course it would happen when it's all erected. Is it going round upstairs?
Very slowly at the moment, it's just coming to a standstill. Can't blow it from here. Is that the string?
No.
No.
That's the wrong thing. We've got the plug in the wrong place. Okay, we're okay.
Right?
Yep, it's absolutely fine.
Okay. As long as that LED, that display doesn't stop the wind speeds.
Because you know what a maniac I am.
I'm more worried about getting hit from behind by things.
Right, well, we've got data at the moment, haven't we?
Yeah.
It's 15 mph.
Right. 6563, 657, was it 72?
Right.
8391.
mph.
Right.
That's 20 now.
Right.
And just slightly under 20. It's difficult to keep at 20. 20 now.
Right.
The vibration of the anemometer unit that you can see is caused by the fact that we used a thin brass strip to mount it. Probably not the ideal thing, but it doesn't really matter. We'll probably use something more firm in the final design. At this point my camcorder battery, which was filming the counter timer, ran flat and turned itself off, so we had to turn off the dual carriageway to fix that problem. 25. Is it on?
Right, yeah.
We've got the red light on.
Yeah.
So far there's been no field gate for me to turn right.
We've lost sync, of course.
Oh, fuck.
Right, recording. Right. Okay. So that's filming that, and away we go.
So we did tests up and down this dual carriageway, going east-west or west-east, and trying to keep the speed steady at 30, 40, 50, etc. mph. Eventually we got home. Do you want to get out and do a tree avoidance?
No, I think I can judge that if you stay in the middle there, you're okay. This one might be a bit low, just
What about this one?
yeah, sure, well, I don't think you'll clear that, you'll probably take an apple with you. Let me put this off now.
So I put the data into a spreadsheet and converted the pulse width measurements back into a frequency using knowledge of the mark space ratio of that reed switch. And this shows the result based upon the measured frequency and the car's speedometer readings, telling us that wind speed is 2.319 times the frequency. So that's quite good. And then we did the corresponding thing, only instead using the blue Kestrel anemometer that we had strapped at the top there. And that produced a rather less satisfactory shaped straight line, but still with the same, basically the same answer, that wind speed equals 2.32 times measured frequency. So that's the calculation we're going to use in the autopilot, in the Micromite software, to get the wind speed. Phew! Well, that was quite a complicated and harassing business, and most things that could go wrong, of course, did go wrong, but eventually we got the answer. Anyway, thanks very much for watching.